All right, let's take a look at the multiple choice of our study guide. Okay, so we took the last year's final exam for C101 from IU and pared it down a little bit to cover the material that we've covered this year. So let's see what we can figure out. So first question. Number one, which of the following represents a physical property? Okay, so I've already got these answers kind of outlined, so that way I can keep myself on track. But let's talk through these. Okay, mercury is a shiny liquid at room temperature. Okay. I mean, shininess doesn't really have to do with the chemical itself. A chemical property in kind of in opposition to this, in the other case, would be something about how it reacts or how it behaves chemically. So typically that has to do with how things are reactive or unreactive and stuff like that. So if something is shiny or bendable or hard or soft or dense or something like that, those are physical properties. So being shiny doesn't really change how mercury is acting chemically, but if aluminum can oxidize pretty easily, that has to do with how things chemically react. Oxidizing is kind of like, you think of it like rusting. A lot of times it's actually picking up oxygen, but we'll find later that oxidation can happen other ways. Sodium metal is extremely reactive with chlorine gas. Okay, yeah, again, reactive, so that's a chemical property. It's about how it is interactive with other chemicals. The unreactive nature of argon gas, the flammability of butane fuel, all these have to do with chemical properties. Okay, so our physical properties like luster and boiling point and melting point and things like that are more about how the substance physically acts rather than chemically. So really, as long as it's not about how it reacts or how it behaves, in other chemical environments, then it's probably going to be a physical property. Number two, which of the following is a pure substance? Okay, a pure substance can be a monatomic element. It could be a diatomic element. It could be a covalent compound. Could be a polyatomic molecule or a polyatomic element. Could be an ionic compound. And so on and so on. But in any case, a pure substance must have a defined chemical formula. In other words, if I'm talking about that chemical, I should be able to say, oh, it's this. It's made up of these atoms of these elements, or just even one atom of one element. Okay? And that formula doesn't change depending on the situation I put it in. So, like, for instance, water is always going to be H2O. No matter what, I can put things in water and make it a mixture. I can have water in the gas phase or the liquid phase or the solid phase. But water is still water, and H2O is still H2O, and that formula doesn't change. Air can come in a lot of different percentages. Mostly it is O2 and N2 with some other stuff in there, but that's at least two different chemicals combined. You can have them in different ratios and still call it air. It's like maybe you have 21% O2 and maybe you have 22% O2. It's still air. That's the name of the mixture, we call that. So it's more than one pure substance. Orange juice and blood, same thing. There's different parts that make up orange juice or blood. If your orange juice is made of exactly one chemical, it's probably not going to taste all that good, or it's not going to be as nutritionally pleasing or something like that. And your blood is made of multiple components. You got the plasma, and you got the platelets, and you've got the red blood cells, the white blood cells, and there's water in there, and whatever else. I don't know enough about blood to continue the list, but it's got at least more than one pure substance. That is for sure. But aluminum whether it's in a block or in the shape of a ring or a nail, doesn't matter. Aluminum is aluminum. It's an element. It is a metal. So this is just one pure substance. So this block of aluminum is our pure substance in this case. Number 3, if 1.31 kilograms of a substance occupies a volume of 960.0 milliliters in relation to water, which has a density of 1.0 grams per milliliter, which statement is true? Okay, well, if we want to figure out whether this will sink or float, or whether it has the same density or the density can't be calculated, we need to try and calculate the density. Density is how much matter you can pack into a certain amount of space, which means it's got to be mass divided by volume. Typically, we use grams per milliliter when we do the density of substances in chemistry, which is why we have the density of water in grams per milliliter over here. So if we want to compare that to this substance, we should also make our units in grams per milliliter. So we have this substance 1.31 kilograms. I want that in grams. Our quick metric conversion chart looks something like this. It's K for kilo, H for hecto, DA for deca, the base unit, D for deci, C for centi, and M for milli. If I'm going from kilograms to regular grams, I'm going 1, 2, 3 spots to the right. You can also do a conversion, say, well, there are 1,000 grams in a kilogram, so I'm going to divide by 1 kilogram, multiply by 1,000 grams, cancel my units, and I get my answer. Either way, we should end up with 1,310 grams of this stuff, occupying a volume of 960 milliliters. So our density is going to be 1310 grams over 960 milliliters. Okay, which is going to be what? Let's punch this into a calculator. 1310 divided by 960 gets us 1.365. 1.365. Okay, without even calculating this too, you might be able to look at this and say, well, top number is bigger. It's going to be bigger than 1 when I divide this out, which is what the density of water is. So this is going to be more dense than water. Things that are more dense will sink, and things that are less dense, okay, whether it's a fluid like air or a fluid like water. So in this case, this is going to sink, not float. We definitely can calculate the density. We've got all the tools we need. It's definitely not the same density as water. If it was less dense, then it would float on the water. The water would be below, but in this case, it's going to sink. Number 4, the density of aluminum is 2.7 grams per milliliter. This is equivalent to how many kilograms per cubic meter? Well, let's see if we can convert this. Okay, the easiest part of this is going to be changing our grams to kilograms. So let's do that first. So our 2.7 grams per milliliter could be written like this. Let's change how we put this. 2.7 grams per 1 milliliter. Okay, there are 2.7 grams in every milliliter that there are. So let's multiply this. Okay, I want to get rid of grams and change to kilograms. So again, you could do your KHDA unit DCM thing up here and just move your decimal point over, but I'm going to show the mathy way this time. So to change from grams to kilograms, I need to get rid of grams. I want to get kilograms. My units cancel because there's one on top, one on bottom, and there are 1,000 grams in 1 kilogram. So this is going to wind up being 0.0027, did my math right, kilograms per 1 milliliter. Okay. Now the big reason why I'm keeping the milliliters kind of on bottom specifically is so that now we can convert that into something else. Something that I would recommend having ingrained into your brain is that a milliliter is the same as a cubic centimeter. Okay, so if I'm trying to get rid of milliliters and I want it to cancel out, usually when I want stuff to cancel, I want it on the bottom. This is already on the bottom. So I need something on the top to cancel it out. I need milliliters up here. And 1 milliliter is equal to 1 cubic centimeter. And if you don't have that ingrained yet, again, I recommend it, highly recommend it, because it comes up quite a bit. So our answer is not really going to change, but it is going to change our units. So this is going to turn into 0.0027. I can't really fit the kilograms in there. Kilograms per 1 cubic centimeter. Okay, so we're not there yet, but we're close. We now have something in some kind of cubic meter. It's just not regular cubic meters yet. So I'm going to clean this up a little bit. Let's do this kind of last step. Our math. So let's cut this all out here. All right, so 0.0027 kilograms are in 1 cubic centimeter. Okay. Now, if I'm going to convert this, what I want is cubic meters. And usually what we wanted goes on top, but in this case, since cubic centimeters is still on bottom, it's being divided, we need to multiply to get rid of it. So cubic centimeters is going to go on top so that it cancels. What I want to change it into is regular cubic meters, m cubed, m to the third. So now I have to figure out how many cubic centimeters are in a cubic meter. Okay, well, let's think about it. Let me actually erase this and let's make some more room because I'm going to need a bigger fraction bar here. Okay, well, a cubic centimeter is really just saying centimeters times centimeters times centimeters. Okay, if I multiplied centimeters times centimeters times centimeters, that would be cubic centimeters. All right, well, in 1 meter, there are 100 centimeters. And again, you could figure that out with the chart, or it might just be good to know. I would recommend having some of the basics, kilo and centi and milli, kind of dedicated to your brain space. So a meter is 100 centimeters. So if I wanted to know what a cubic meter is compared to a cubic centimeter, well, if I had 1 meter times 1 meter times 1 meter, 1 meter cubed is just 1 meter cubed. But taking that 100 centimeters and cubing it gets me something different. It would be like saying 100 times 100 times 100. 100 centimeters times 100 centimeters times 100 centimeters gets me some number of cubic centimeters that are in 1 cubic meter. Okay, so I'm not leaving it as 1 cubic meter just for kicks and giggles. It's because I'm saying this is how many centimeters, cubic centimeters would fit in this, and it just happens to be that I'm using 1 meter as the reference point. So when I cube it, it stays the same. Let's move this out of the way. So now if I take 100 times 100 times 100, or 100 cubed, 100 times 100 times 100, we get, looks like, 1,000,000. Okay, in other words, 10 to the 6th. So I'm going to write out 1,000,000. But we're going to change it to scientific notation at the end here. Oops, I don't need my bar to be quite that long anymore. So my cubic centimeters unit goes away. And if I take my 0.0027 kilograms times 1,000,000, what we're left with is 0.002, oops, 0.0027 2700 kilograms per cubic meter. Right? If I clean up my units a little bit, I don't really need to have this one explicitly written down here. It was just to help me cancel my units. So let's change this around here. Let's write this as kilograms per cubic meter like that. Okay, which, if I want to write it in scientific notation, is going to be, got to move 3 spots, 2.700 times 10, and I'm moving that spot to the left, which means my number is actually bigger than I'm writing it. So I want this to be positive so I can remake my big number if I need to undo the scientific notation. My units are still kilograms per meter cubed, and that's what we should get. 2.7 times 10 to the third kilograms per meter cubed. The only difference is sig figs. They started with 2 sig figs, so I should really cut those out. So it should just be 2.7 times 10 to the third like that. But we get the same number. You'd be able to find the right answer that way. All right. Which of the following is an alkali metal in the 4th period of the periodic table? Okay. Well, alkali metal is just talking about a certain group on the periodic table. Okay. A group is another name for a family, which is another name for a column, which goes up and down on the periodic table. Okay. Thankfully, a lot of the columns on the periodic table have names that are just basically the top element. So like column 13 has boron at the top, so it's called the boron group. The next one is the carbon group, and then the nitrogen group, and then the oxygen group. After that, though, we have some individual unique ones. So the 4 I would say that are best to know, column 1 is the alkali metals. Column 2 is the alkaline earth metals. Column 17 is called the halogens. And column 18 is called the noble gases. All right, those are the important ones to know. All right, now periods are just the rows on the periodic table. They don't really have any other synonyms. We just call them rows. So they're going left to right on the periodic table. So we're looking for something that is the 4th row down, is in the 1st column on the left of the periodic table, which ends up being potassium. Potassium is an alkali metal in the 4th period. It's in the 1st column. It's in the 4th row. It's the only element that takes up that spot. Okay, number 6, ionization energy, blank from top to bottom in a group, and blank from left to right in a period on the periodic table. Okay, so ionization energy is biggest in the top right of the periodic table. So this is my kind of hastily made periodic table here. Ionization energy is highest up in the top right. So it should be increasing this way and this way. So it should increase from from bottom to top. So it should decrease from top to bottom. Okay. And as we go from left to right, it should increase, which is what we got here. Okay. So our ionization energy is highest in the top right, and so we're increasing as we go up and right, but since it's saying top to bottom, it's kind of backwards, which is kind of annoying. It's just kind of a wording question more than a chemistry question. Okay, so ionization energy decreases from top to bottom. Again, group is just a column, and increases left to right in a period across a row. Which color of light is composed of photons having the largest energy? In number 7. Well, our electromagnetic spectrum goes from in the visible range, red to orange to yellow to green to blue to violet. I don't have my yellow color on my palette right now, so I'm just going to skip it. Green, blue, and then violet. Okay. That increases in energy going this way. Okay. As we increase in energy, we also increase in frequency. Okay, a wave that oscillates more frequently, that is up and down, up and down, up and down, up and down really fast as the wave moves. That's a high frequency, and that's a sign of high energy. All right. And in order to have a high frequency, you've got to have a small wavelength. So as we go across this way, we are decreasing wavelength. It's not let me right there, so let me scroll this down a little bit. Okay. In equations, E is usually energy. We've got this nu, which is kind of like a messed up V for frequency, and then the Greek letter lambda for wavelength. Okay. If you were asked about other invisible kinds of light, so not the red and orange, the rainbow colors, you might think of some things that are kind of pre-red, that are lower energy, things like radio waves and microwaves. Okay, and if you're thinking of stuff that's higher energy than violet light, past the visible range, you might think of stuff like, well, actually, here, let's start with this. Ultraviolet, X-rays, and then gamma rays. Also, infrared is lower. So infrared is a little bit lower energy than red, and ultraviolet is a little higher energy than violet. All right. Number 8, calculate the energy in joules of red light with a wavelength of 660.5 nanometers. Okay, so let's see. Let's break out some energy, light equations. So we've got E equals Planck's constant, H, times the frequency, nu. Okay, or we could write it as speed of light, c, is equal to the frequency, nu, times the wavelength, lambda. And we can kind of swap stuff into these equations if we need to. Like if you notice, we could solve for frequency here and put that in and substitute it. So we don't want to use frequency, we can use that there. So since we're calculating energy, we probably want an equation like this. But our issue is we have a wavelength, and that's it. We're only given a wavelength. So if I wanted to use this equation here, I would need two things. I would need Planck's constant, and I would need the frequency. Well, I don't have the frequency. So what I can do instead is say, hey, I don't know what this frequency is, but I know what the wavelength is, and maybe I can kind of replace it. So if I were to solve for the frequency to kind of replace it, frequency would be equal to, well, I divide both sides by lambda. We cancel on that side, and what I'll be left with is c over lambda. Okay, so that piece can go in for my frequency here. So instead of writing frequency, I could write c over lambda. So my new equation is going to be E, the energy, equals H times c over lambda. Okay, now they don't give me H and they don't give me C, but that's okay because those are both constants. Okay, they're just a single number that would help to know. I would give you the value if you needed it because it's just a memorized number otherwise, but it might be good to know. So H, let's do the color. H is 6.626 times 10 to the negative 34th, if I remember correctly. And its unit is joule seconds, joules times seconds. And then the speed of light is 3 times 10 to the 8th meters per second. Okay, now, whenever we're dealing with light, especially visible light, we'll usually end up with a different prefix on our meters other than just regular meters, which is something we have to kind of watch out for. My pen stopped working. That's not good. So we're going to have to convert some stuff to get this to work out. Okay, we won't just be able to plug in nanometers and hope for the best if I want things to cancel out correctly. Okay, so let's make some room here. Except my pen is still not. Oh, it's back. It's back. It's back. Okay, cool. Let's make some room. I'm going to erase these. We'll plug in what we know. Okay, so E equals H, which is 6.626 times 10 to the negative 34 joules seconds, times my speed of light divided by the wavelength. So I'm going to write 3 times 10 to the 8th meters per second. Okay, and that's going to be divided by my wavelength. Okay, and really, since this is all multiplied together, I'm just going to kind of put it underneath all of these so I can kind of deal with it last. So this is going to be my wavelength, which is 660.5 nanometers, and that is not going to work out in the long run. Let me show you why. So if I go to cancel my units here, let's see, I've got joule seconds, so seconds is being multiplied, and over my speed of light, it's being divided, so on top and on bottom, those seconds cancel and go away. I want energy in just joules. So, hey, I'm on my way to getting joules alone. But if I want this meters to cancel out, it's going to cancel with this. So I either have to change my speed of light or I've got to change my wavelength here to have the same units. I would probably change the wavelength. I think it's going to be easier. So I want to change this guy to be regular meters instead, so that way it matches and cancels out. So what's an easy way to do this? Well, nano is an important prefix to know, just off the top of your head. So I would commit that one to memory. And you start a list. So let's see. So things to commit to memory. Okay, like column 1 and 2, column 17 and 18. 1 centimeter cubed is 1 meter is 1 milliliter. Things like that. It'd be good to commit to memory. The order of energy of the electromagnetic spectrum would be pretty good to memorize. Let's see. Okay. And again, our prefixes for kind of common metric stuff. So kilo is common, centi is common, milli is common, and nano is common. So let's convert this guy. So for now, I'm just going to call this lambda for my wavelength, but let's convert it. I'm going to use this space down here because I got room. We'll kind of erase it later. So 660.5 nanometers. I want to get rid of my nanometers, nm. I want to get meters so that these units cancel out. So the question is, how many nanometers are in a meter, or how many meters are in a nanometer? Nanometer is tiny. It's very tiny. It's very small. So I'm going to say how many nanometers are in a meter. Okay, there are 10 to the 9th nanometers in 1 meter. You could also say that 10 to the negative 9th meters is 1 nanometer. That also works. Okay. You could also say, oops, you'll sometimes see this as 1 times 10 to the 9th, because having just the 10 to the 9th there kind of makes people uncomfortable sometimes, but it means the same thing. 1 times that is just going to be, that. So I'm going to leave it like this. So 10 to the 9th nanometers is going to be 1 meter. So if I take 660.5 divided by 10 to the 9th, I should get what I need. 660.5 divided by 10 to the 9th. Should be 6.605 times 10 to the negative 7th. Uh-oh. Oh, I'm erasing. 6.605 times 10 to the negative 7th meters. I basically moved my decimal point 9 spots to the left. I think. That should be. Okay. So this is what I'm going to plug in for my wavelength here. So this is going to be 6.605 times 10 to the negative 7th nanometers. Oh, no, sorry, meters. I need the units to cancel out. Meters, regular meters. Ooh, okay. Regular meters cancel. So our only unit yet left is going to be joules. So the last thing we need to do is just crunch all these numbers together. So when you're doing stuff like this, especially when you have scientific notation on the bottom here, don't forget to use parentheses in your calculator. So let's do 6.626 times 10 to the negative 34th times 3 times 10 to the 8th power divided by, okay, and then again, make sure you keep this whole thing in parentheses, 6.605 times 10 to the negative 7th. All right, and we should get something around 3.009 or 3.01 times 10 to the negative 19th. Our unit is joules. So again, be careful about your units and be careful about your scientific notation. Let's get rid of this stuff down here. Number 9, according to the Bohr model, when a hydrogen electron makes a transition from n equals 4 to n equals 2, from the 4th energy level to the 2nd energy level, which of the following statements is true? This n equals 2 and n equals 4 is just a way of saying the different energy levels. So when you see like the 1 in 1s2, or the 2 in the 2p6, or the 3 in the 3d10, those big numbers out front are just what the energy level is, kind of as we go out farther and farther from the nucleus, and sometimes we call that n. It's a quantum number that we don't really cover as much nowadays, because knowing the quantum numbers and how they work doesn't help you understand the atom all that much more. It's just kind of more memorizing things. So from n4 to n equals 4 to n equal 2 means basically we got our nucleus here and we've got our energy levels. This is my first energy level, and this is my second energy level. This is my third energy level, and this Bohr model of the atom is obviously not our current model, but it helps us visualize things like this when we're talking about electron excitations and transitions. So if we're going from the 4th energy level, let me do a different color, 4th energy level to the 2nd energy level, we're moving closer to the nucleus, okay, which means we're going to a place that's more stable, okay, which means that our electron should be releasing energy. So energy should be emitted, which means released, okay, Energy would be absorbed if we're moving our electron out farther from the nucleus where it's less comfortable. If the electron is kind of obeying the Coulomb's law of attraction and attracting to something that's positively charged and moving closer to it, then it's going to be more stable. It's going to be lower in energy. So our electrons lose energy as they release energy. Okay, and this is what we basically have happen when we do a flame test or other excitations like gas spectrum tubes, when we give something energy in the form of heat or light or electricity and get them to release light. And the color of light tells us how big of a jump that electron made. Okay, so in this case, energy is emitted as the electrons lose that energy as they become more stable as they move closer to the nucleus. Number 10, the size of boron is blank than the size of oxygen and blank than the size of aluminum. So let's see, boron is over kind of on the right side of the periodic table. Oxygen is farther to the right, okay? And aluminum is right underneath it. Okay, atomic radius, if I can draw my poorly made periodic table again. Atomic radius is biggest down in the bottom left. Okay, so boron is going to be bigger than oxygen because their electrons make it out to about the same distance from the nucleus. Boron ends at 2p1 and oxygen ends at 2p4. So they both make it out to the second energy level. Having more electrons in these p orbitals doesn't really make the reach go farther. So it doesn't mean that like oxygen is going to be bigger because it has a couple extra electrons. They're kind of just taking up more space, the same distance out from the nucleus, roughly. Okay, but oxygen does have more protons. It has more positive charge, which means it's going to be pulling in those electrons a little bit harder than boron would. So oxygen is going to kind of shrink in comparison to boron size. So even though their electrons go out to the same energy level, they're closer into oxygen because of that attraction to the nucleus. Okay, so boron is going to be bigger than oxygen because it's got less protons to pull in that electron cloud. Okay, but aluminum is going to be bigger than boron. In other words, boron is smaller than aluminum because aluminum is another road down. It's a little bit farther down on the periodic table. It goes out to the third energy level, which means it's a little bit bigger. It goes a little bit farther out in the electron cloud when it fills up its electrons. So boron is larger than oxygen, smaller than aluminum. Number 11, which of the following species does not match the electronic configuration? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Well, if it's ending in a p6, that's a noble gas. At least it should be. Let's see. Or it's matching a noble gas configuration. If we do our little shortcut, the P block is on the right side of the periodic table. It's kind of after the valley we call the transition metals on the right side. It's that big block on the right side with the helium as that kind of cap. Okay, now each column is kind of adding one more electron as we go from left to right. So as we go from boron to carbon to nitrogen, we're kind of adding in another electron, another electron, another electron. So our last column in the periodic table, column 18, should have the ending p6. Okay, it should be the sixth electron in the p block instead of p orbitals. So this is going to be something in column 18. Okay, specifically because of this p6 part. Okay, it's going to be the sixth element in the p block, which is the last column of the p block. Okay, the 4 out front tells us it's going to be in the fourth energy level of the p block. And for the p block, that is just the fourth row of the periodic table. Be careful with the D and F blocks. They fall back one each. So like the fourth row of the periodic table is actually the third energy level for the D block. And the fifth row of the periodic table the sixth row of the periodic table is going to be the fourth row of the F block. So be careful of that. It's not just like it's this row, so it's this number. But with the S and P block, it does work like that, which is nice. So this is in column 18, and it's in row 4. Okay. So if you're going for the neutral element there with the same number of protons and electrons and all that stuff, we would land on the element krypton. Okay, but something could still have this electron configuration of krypton by becoming an ion. That's what a lot of atoms do to make compounds, especially when we put a metal and a nonmetal together. So if we have something like arsenic 3 minus, okay, that just means it has 3 extra electrons. If you look at where arsenic is, it is in the P3 area of the periodic table. So if we had an extra 3 electrons, giving a negative 3 charge, boop, 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 it bumps over to the right to be in krypton spot. Okay, that doesn't mean it changes into the element krypton. It just means it has the same electron configuration. So arsenic is good to go. It would usually end at 4p3, but because it has 3 extra electrons that we see from this negative 3 charge, okay, that means it's going to have the same electron configuration as krypton. For bromine, negative 1, it's gaining 1 electron. If we bump bromine's electron configuration 1 over, krypton's right there. So that looks good. Strontium 2 plus means it's lost 2 electrons. So if we bump 2 spots back from strontium, we end up at krypton. So that one's good. Okay. Selenium 2 plus. If selenium loses 2 electrons, it bumps back to germanium spot, okay, which is in like a P2. It bumps back from a 1, 2, 3, 4. Bumps back from a 4p4 to a 4p2. So instead of gaining 2 electrons to be like krypton, it loses 2 electrons, but puts it the kind of opposite way. So selenium 2 plus is not the same in electron configuration as krypton. So that's our answer here. Okay, number 12. Which of the following statements best describes an ionic bond? Well, it's going to be a give and take of electrons. We should end up with charged ions as a result, positively charged cations, negatively charged anions, held together by electrical forces. The electrostatic force we call Coulomb's law. So get my pen back. So yeah, this one looks best to me. Equal sharing of 2 electrons between 2 adjacent atoms would be more like covalent. Bonding type between 2 metals would be like metallic bonding. Bonding type present in bound non-metal atoms, kind of like, it sounds like covalent. So yeah, no, this is definitely it. Number 13, if the electrons are shared equally between the 2 atoms, the bond is called, hey, nonpolar covalent. Now, if they are shared unequally between the 2 atoms, it would still be covalent because they're still being shared. That's what makes it covalent, okay? But sharing them equally is what makes this nonpolar covalent. There's no dipole. There's no polarization of the electron cloud across the bond. So we have a roughly kind of equal electron density around those atoms. Which of the following name and formula pairs is incorrect? Well, rhenium, let's see, 7 oxide would mean our rhenium has a positive 7 charge, and our oxide usually has a negative 2 charge. So here's a little trick you can use. We have this thing called the ion crossover method, where you can just kind of switch the charge over to be the subscripts of your formulas. So it basically is the short way to figure out how much of each element you need to cancel the charge of the other. So Re2O7 looks pretty good to me. The only thing that doesn't work about the ion crossover method is if you have, well, actually, let's look at the next example, and I'll show itself. Calcium oxide, Ca2 plus O 2 minus. Okay, if I do the little crossover method here, I put the 2 over here, put the 2 over there, so I get Ca with the 2, O with the 2. And so my Formula is Ca2O2, which doesn't totally seem to make sense because if our calcium has a positive 2 charge and our oxygen has a negative 2 charge, those should cancel on their own, just one atom of each, one ion of each. So I don't need 2 of each of them. So we can reduce these down. Okay, if you have a 2 and a 2, or a 3 and a 3, or a 4 and a 2, or a 6 and a 3, they can be reduced. Okay, so reduce those down as you need to get kind of the lowest common denominator. In this case, 1 of each, so it's just CaO. That looks good to me. Potassium carbonate. Carbonate is a polyatomic ion with a negative 2 charge, which is why we need 2 positively charged K potassium ions to cancel out that charge. And carbon tetrachloride is covalent. The prefix tetra tells us 4. We don't use mono on the first element just for whatever reason. It's kind of tradition. So carbon tetrachloride is talking about 1 carbon, 4 chlorines. So what's that leave? Copper dichloride. Well, this seems fine. I mean, CuCl2 would be 1 copper and 2 chlorines, but this name isn't written correctly. If we were doing this formula, CuCl2, copper is a transition metal, and chlorine is a nonmetal. So, first of all, this is ionic, not covalent, so you shouldn't be using that prefix. But, maybe we should give them the benefit of the doubt. Maybe there's a close enough electronegativity difference between these two where it's not really ionic or something like that. But the kicker is the copper being a transition metal. This is one of those metals that can have a couple different charges depending on how it gives and takes electrons. Okay, so in this case, because our formula is telling us that we are bonding with 2 chlorine atoms, each of these has a negative 1 charge. So altogether with 2 chlorine ions, that makes a negative 2 charge. So if we need to cancel out a negative 2 charge with 1 copper atom, that needs to have a positive 2 charge, okay, which we need to state in the name so we could be able to figure out what the formula is based on the name. Okay, so I would have to write this as copper with a Roman numeral 2 to say I have a positive 2 charge, and then chlorine becomes chloride. Okay. Now, this is something you have to be careful about. The Roman numeral is not how many atoms of that element you have, it's how positive it is. Okay? You might also see something called the oxidation state be brought up, and that's maybe a little bit more technically what it's supposed to show, but we'll talk about that when we talk about oxidation reduction reactions. For now, we just think of it as the charge, and it's basically the same thing. Number 15, which compound listed below has a bond angle of 120 degrees around the central atom? Well, if you're math-minded, and you don't have your VSEPR stuff kind of ingrained in your brain, like probably most kind of students, you don't really get this ingrained unless you really do this for a while. Well, a circle is 360 degrees. So 120 degrees would come from splitting that 3 ways. So our compound is going to look something like this. It's going to be trigonal planar, or at least the electron geometry is going to be trigonal planar. Okay, so that way we have 120 degrees between each electron domain, be it an actual bonded atom or a lone electron pair. Well, CCl4 would be something like this. 1 carbon bonded to 4 chlorines. That's going to end up tetrahedral. It's got 4 things bonded. It's not trigonal planar, whatever it is. NH3 may have 3 things bonded to it, but it also has a lone pair of electrons. It's got to have its own spot. That's 4 electron domains. Not what we need. We need only 3 electron domains for this bond angle of 120 degrees. CO2 has 2 bonded atoms. That's linear. That's not going to be trigonal planar. And then H2O, okay, not only does it only have 2 atoms, but it ends up bent because it has 2 electron pairs just hanging out on the center atom. So it's got 4 electron domains total. So that leaves our last option, which is CH2O, which looks something like this. Carbon in the center, H, H, And then to get our oxygen to an octet, it needs a double bond. Okay, so CH2O is our answer. Number 16, in a molecule having 3 pairs of electrons around a central atom, Sn equals 3. This is just a kind of a way of saying, how many things you have around the central atom. They call this the steric number in the textbook. But we don't really talk about stereochemistry and kind of where that becomes more useful in this class. That's more of an organic chemistry thing. So I tend not to use the SN thing because it's just one more thing to know. And you could easily just say 3 electron domains. But that's all this means. We have 3 electron domains. We got a trigonal planar shape. How many lone pairs of electrons does the central atom have? Well, if the shape of our molecule is trigonal planar, okay, that means that we've got 3 bonded atoms to our central atom. Well, we can't really have 3 things bonded and still be a trigonal planar shape if there's other lone pairs on here. Okay, if I add another lone pair in, kind of like this NH3 up here, it's going to bump those atoms out of the way, and they're not going to be sitting flat in a plane anymore. The only way to get a trigonal planar shape is to have just 3 bonded atoms. So there must be no lone pairs of electrons. This cannot work. Otherwise, we end up with a tetrahedral electron geometry, and it pushes them out of the way, so they're no longer in line with each other. 0 lone pairs. Which drawing best accounts for the polarity of methanol, CH3OH, and the bond polarities that make a major contribution to the overall molecular polarity? Well, let's see. All these molecules look basically the same. Okay. And we've got an O in there. That's our most electronegative atom. Okay. So that's going to be kind of drawing the electrons mostly towards it. So what I don't like right off the bat is this right here, where our dipole arrows are pointing away, indicating that our oxygen is just gonna, it's gonna share its electrons more and kind of let them loose to the hydrogen and the carbon. Not gonna happen. The oxygen is too electronegative. It's up in the top right of the periodic table, at least a lot more than carbon and definitely more than hydrogen. So that one's not gonna fly. Okay, same thing with this one. Okay, and it's almost identical. The only difference is they tried to sneak this in and be like, well, it's partially negative because oxygen's electronegative and it's going to pull the electrons closer to it. But they put the bond dipole arrows the wrong way. Shame, shame. So not going to be either of these. So that's between these two. Well, it seems like the only difference from drawing to drawing, if we kind of check it over, is these partial charges. Okay, the bond dipoles are indicating that oxygen is kind of the most electronegative thing. It's pulling the electrons closer towards it, which is good. Okay, and overall we have a net dipole that is going up kind of this way because of that pull of electrons towards the oxygen atom in these cases. But in this case over on the left, where again it's saying the oxygen is partially positive and the other things are partially negative, which is not true. We should be pulling that negative charge away from the carbon and the hydrogen. So B, number 2, is our best answer. Number 18, the main reason why carbon tetrabromide is a solid at room temperature when compared to carbon tetrachloride, which is a liquid, is because what? Well, we kind of drew these out. Carbon is in the middle of both of these, and there's 4 things bonded to around the center of these. 1, 2, 3, 4. Okay. Carbon and bromine and chlorine are all nonmetals, so these are both covalent. So it's not like a difference like, carbon tetrabromide has stronger bonds because it's ionic. Well, no, they're both covalent, so there's no difference there. Okay. But that doesn't mean that the covalent bonds are the same themselves. If I have this guy bonded to my bromine atoms, and if I compare that to chlorine, well, chlorine is more electronegative than bromine is, which is interesting. Okay, which means chlorine is going to be a little more tight with its electrons. Now, both of these are nonpolar. Because even though these bonds are polarized towards our bonded atoms, our halogens, the bromine or the chlorine, our column 17 guys are always, well, mostly very electronegative. So got our bond dipoles go in those directions. Okay, so overall they're nonpolar because it's a symmetrical pull of the electron cloud towards every single atom. There's no lone pairs to throw off that symmetry. So they're nonpolar molecules. They aren't going to stick very well to each other via intermolecular forces. But if they're covalent and we end up with something being a solid and something being a liquid, there's got to be some attraction from one thing to another. So the attraction is going to be thanks to dispersion forces or London dispersion forces, or instantaneous dipole-induced dipole forces, which basically just means as these molecules get close to each other, oops, I accidentally got a polarized electron cloud, and then now I attract to something else and induce a dipole in something else for just a moment. Okay, well, what's going to be best at dispersion forces is something that can move its electron cloud around pretty well. Things with a higher electronegativity and a smaller size, like chlorine, is going to be very tight about its electrons. They're going to keep them close in. But bromine has a bigger electron cloud. It's a little more loosey-goosey, a little less electronegative. So it's going to be a little bit easier for its electrons to shift around and polarize. So even though these are both nonpolar on their own, when I start to bring molecules of carbon tetrabromide together, the electron cloud around that molecule is a little bit easier to bully and push and shove and send it kind of more towards one side or the other to get it to polarize. That means it's going to have a higher kind of polarity in the moment, which means stronger attractions, more like a partial positive and a partial negative charge. And so it's going to have stronger dispersion forces that hold it together. Yes, so carbon tetrachloride has weaker dispersion forces than carbon tetrabromide, which has stronger dispersion forces. Number 19, which of the following chemical substances would you expect to have the highest boiling point? You may consider molecular mass and the degree of intermolecular forces as primary controlling factors. Okay, well, what they mean by molecular mass or molar mass being a factor, imagine you have two balls you want to make act like gas particles. So one of them is a ping pong ball and one of them is a bowling ball. Well, if you want your ping pong ball to act like a gas particle, you're going to throw it up in the air and say, fly, be free, and then you just whip it, and it goes flying around, and eventually it's going to come back down. But it's going to be a lot easier to throw up into the air and be like, oh, it's a gas particle, compared to that bowling ball, which is very heavy. So if you're like, fly, and heave that bowling ball up into the air, first of all, get out of the way because it's coming back at you. It's also going to be a lot harder. Okay, bigger molecules are going to be harder to get moving as more like a gas state. Okay, to get them to move more freely, they need to have higher energy. Okay, so you can think of it like that. So we could just go and say, well, which one of these is the biggest molecule? Well, CH4 is the smallest because it's got the least number of atoms. CH3 is a little bit bigger. It's got another carbon and a couple other hydrogens. CH3 is a little bit bigger than that, and CH3CH2OH is about the same size as the CH3CH2CH3. So these guys are about the same. Okay. Now we could go and add up all the CHs and Os of these guys and see, oh, which one has the bigger molar mass? But that only gets us part of the way, because the bigger factor here is going to be the intermolecular forces. Okay. The size or the mass of the particle can help us figure out what's easier or harder to boil, what's easier or harder to make into a gas. Again, with that kind of bowling ball example. But we also have to consider kind of the force that attracts particles together and keeps them from flying away. So in the ping pong and bowling ball example, it's not great for thinking about intermolecular forces because the force of gravity is the same on both of them, whether it's a ping pong ball or a bowling ball. Okay, with intermolecular forces, we change how attracted they are to come back to each other. So in the case of this A versus D choice, we're looking for which has the stronger intermolecular forces. Well, our D option, okay, has an oxygen in there that's very electronegative. That's going to be a polar end of the molecule, which means we're going to get some dipole-dipole action, maybe even hydrogen bonding, okay, because we've got that OH there. So as a result, stronger attractions, harder to get that to boil into a gas and get the particles away from each other. Whereas something like a CH3, CH2, CH3 is all pretty nonpolar. C and H are pretty close in electronegativity, so there's not going to be a whole lot exciting going on with attractions between those molecules. It's going to be weak dispersion forces. So, did I? I think I circled the wrong one on this. It should be D. Yeah, I think I just circled the wrong one. Now I'm wondering if something else was supposed to be C and I marked it D, or if I just marked C twice. Well, now I'm going to have to go fact check myself. So let's go check the answer key. 18 was C, 19 was D, 28 was C. So starting with 18, C, D, C. C, D, C. Okay, yeah, I just marked it wrong earlier, which is ironic because I marked them so that I wouldn't do that exact thing and mess it up. But hey, we came to the right answer. I just had to talk myself out of making sure I didn't just rely on whatever I circled first. Number 28, how many moles of gas are found in a container that occupies a volume of 5.50 liters with a pressure of 0.335 atmospheres at 25 degrees Celsius? It's time for the ideal gas law. So we have our gas law, which is PV equals nRT, aka PivNert. We have a pressure. We have a volume. We have a temperature. We can pick a gas constant for atmospheres. All that's left is to find moles. Nice, pretty cool. The only thing we really need to change is this. Only Kelvin. We can only have Kelvin in PivNert. So let's plug in what we do know. So 0.335. I'm going to leave out the units because they'll all work out in the end, right? I need space. 5.50 liters equals, and which we don't know, are the gas constant is going to be 0.0821 for atmospheres. And that's where our big crazy unit would be that fixes our other units. And then 25 degrees Celsius changed to Kelvin would be 25 plus 273.15. Okay. From there, you just plug in your numbers and multiply and divide. So we'll take 0.335 times 5.5 and then divide it by whatever we get over here. This 0.0821 times, this is going to come out to be about 298.15. Take that and then take this answer and divide it by what we get over here to get N isolated, just get moles. And we should end up with this answer here. Okay, now because that's just multiplying and dividing, I'm going to leave that one there, and hopefully that will be enough. The volume of 9.5 grams of fluorine gas, F2, at STP is what? Well, let's try looking at PivNert. PV equals nRT. Well, at standard temperature and pressure, we know the standard temperature is 0 degrees Celsius, aka 273.15 Kelvin. And pressure is 1 atmosphere. Okay, we can pick an R constant to fit that right there, and we can figure out moles by changing our grams into moles. So the last thing we look for is volume. Okay, there are two ways you can do this. One way is using the ideal gas law like this. Okay, there's also a trick. So because the math is basically kind of the same as this, just all we'd have to do is take this 9.5 grams and use the molar mass of F2 to convert it into moles, and then we just plug and chug. But let me show you the shortcut. This only works when we are at standard temperature and pressure, okay? Because it's a nice, easy relationship between all these things. If we know the temperature and we know the pressure, and we have a certain number of moles of gas, everything else is controlled, so it has to fit a certain volume under those conditions. So let's take our 9.5 grams, and we're going to convert it into moles. That's a really bad fraction bar, which we'd have to do anyway. So whether you do in Pipnert or this trick I'm going to show you, that's fine. So this is grams of F2, fluorine gas, F2. We're changing this to moles of F2. All right. The molar mass of F2 is going to be 2 F atoms. They're each about 19 grams per mole, so that comes out to be about 38 grams of F2 for 1 mole of F2. Okay, so we could find the answer there and then plug that into the N of PV equals nRT. But instead, we have a relationship. This, again, only works at STP and only if my pen is working. But 1 mole of gas at STP must fill 22.4 liters of volume under ideal conditions. Okay, which means we basically get another conversion factor we can throw into our unit conversion here, our little stoichiometry problem. So rather than having to do the whole PV equals nRT thing, once we have the right number of moles figured out, canceled out our grams. Okay, I can just continue with another fraction bar and say, well, hey, for every mole of gas that we have, whether it's F2 or H2O or C3H8, that's going to take up 22.4 liters of volume. So I take 9.5 grams, I divide it by 38, I multiply by 22.4, and I get 5.6 liters. Okay, which is exactly what our answer should be. So you can try this with PV equals nRT and you should get the same answer, but this is just way faster. Number 30, 0.123 grams of a gas occupies a volume of 124 milliliters at 120 degrees Celsius and 1 atmosphere. The possible formula of the gas is what? Well, this kind of sounds like we were supposed to just divine some information out of nowhere. It's like, Billy's walking down the street and he has blue eyes. What's the mass of the sun? Okay, but we can figure this out. Let's kind of just deal with the information that we have. We have grams of a gas. We have milliliters. We have a temperature. We have a pressure. Okay, so really we have everything that we would need in order to plug in for PV equals nRT. I mean, we could change this to liters. We could change this to Kelvin. This would be our pressure. We could convert this into moles if we knew what it was, but we can't. So maybe that's where we should start. Maybe we should start by trying to figure out what N is supposed to be, how many moles we have, and then we can use that grams. Let's try that. Let's erase that there. Plug in what we know. Okay, our R constant uses liters, not milliliters, so I'm going to change this to regular liters. I'm moving it 3 spots to the left. Okay, and this plus 273.15 is going to be our temperature. So 1 atmosphere times our volume of 0.124 liters is going to be equal to some number of moles I don't know and I can't convert to because I don't know what the stuff is. That's what we're trying to figure out. Times my gas constant for atmospheres, which is 0.0821. All right, and then 273 plus my 120 is going to be 393.15. Kelvin. Okay, if I punch this stuff in, I'm going to take 1 times 0.124, which is just 0.124. I take that 0.124 and divide it by 0.0821 and by 393.15, or you can multiply them first and do it like that. I get 3.84-ish times 10 to the negative third. So N equals 3.84 times 10 to the negative third. There we go. Okay. So that's good. And that should be moles. All right. Possible formula of the gas is what? Well, how do we figure out what the substance is? Well, I mean, I have moles now. I have grams. What do we use grams and moles for? We could use it for the molar mass. Grams per mole is what molar mass is. So if I take my 0.123 grams of this stuff that apparently fits in 3.84 times 10 to the negative third moles and figure out what that is, that will tell me my molar mass, which I'm going to use kind of this curly M for. The textbook uses a big capital double M, but that kind of bugs me because it looks like two variables next to each other. So 0.123 divided by, put it in parentheses, 3.84 times 10 to the negative third gives me 32.03 grams per mole. Okay. Well, if I look at these gases and I figure out the molar mass, you have to go and add them up. But let's see, chlorine, each chlorine has a molar mass of about 35. That's going to come out to be about 70 when I add up 2 of them, not chlorine, not Cl2. CH4 is 1 C4H's, C is 12 grams per mole, H is about 1 gram per mole. So that's going to come out to be about 16 grams per mole. Nope. And then CO2 is, let's see, C is 12, O is 16. So that comes out to be about 44 overall. O2, on the other hand, is 2 atoms, which each have a molar mass of 16. So total would be about 32 grams per mole, which is what we got here. So our O2 would have about a molar mass of 32 grams per mole. Nice. So a heck of a lot going on in this problem just to figure out that. Okay, but hopefully it makes sense how we got there. Number 31, under what conditions would a gas be most soluble in a liquid? Okay, now we haven't really talked about solubility strictly yet, and there are some things that help things be dissolved in others, but I think that we can work this out just using our brains. So let's think. If I want something dissolved in something else, it has to go and cooperate with other substance. That means it has to, have some similar attractions to that substance. Otherwise, it would rather go hang out with itself instead of hanging out with particles of the other substance. And if it's doing that, that's not really mixing. So it's got to be able to behave. It's got to be able to kind of work with other particles. Okay. It also can't be so energetic that it just escapes. So if we're trying to shove a gas into a liquid, even if they have strong intermolecular forces, there's a good chance they're going to try and get away just because they want to be free moving, where we're trying to just shove them into a liquid. So how do we get a gas to behave in a liquid, not just fly away? Well, if we had a high temperature, the gas particles are definitely going to get the heck out of there. So high temperature is how we make sure a gas doesn't dissolve in a liquid. So instead, it's probably going to be more like a low temperature. Okay. If I'm increasing the pressure, that means I'm pushing down on stuff harder. I'm keeping them closer together. So that would seem pretty good for keeping a gas in a liquid. If I had low pressure, I'd just kind of like, let things go. And so the gas is going to be like, oh, sweet, there's room to get out and there's nothing keeping me here. So I'm just going to, see ya, escape the liquid. So low temperature and high pressure is going to be the best way to keep the gas moving slow enough to kind of keep it among the other liquid particles without escaping, kind of keeping them attracted to each other. And high pressure is going to keep it nice and close together and keep them from kind of just escaping out. There's going to be kind of a barrier of things they have to push against to fight their way out of the liquid. Okay, so that's kind of the best way to make a gas most soluble. Okay, funnily enough, this is also one of the best ways to make a gas act really instead of ideally. So it's kind of something to think about. It's kind of interesting, since that's all about how stuff attracts to each other and how the particles are close to each other. You know, dissolving is really about how things attract to each other within intermolecular forces. So it kind of just so happens that making a gas behave really like a real gas, like in actual particles, has to do with intermolecular forces. Wow! Number 32, if 125 milliliters of a 2.0 molar stock solution of NaCl was used to prepare a 500 milliliter solution, what is the concentration of the diluted NaCl solution? So here's the thing. There's an equation that floats around. That's M1 V1 equals M2 V2. Okay? When we call it the dilution equation, it's not really like a law as far as I know, or like a a special theory equation. It just kind of works well. Molarity is in units of moles per liter. Volume is in liters equals moles per liter times liters. So this kind of looks like nothing much happens. You might even kind of make comparisons to Boyle's law. If you remember this gas law, P1V1 equals P2V2. Okay, we end up kind of changing the pressure or the volume of a gas, and as one goes up, the other goes down. Okay, with this dilution equation, this is kind of the best way I think of it. Okay, if molarity is how many moles there are per liter of solution, whether we add in more liquid or whatever to dilute it, that's not going to change how many moles of stuff in there are. It just changes how concentrated it is compared to the total volume of the solution. So I can take a can of Pepsi, and I can pour it out into a flask, and I can add a whole bunch of water to it and dilute it down. So overall, now if I take a sip of that nasty Pepsi water solution, it's not going to be as sweet tasting or as kind of tangy tasting. It's not going to have as dark of a color, but all those chemicals that started in there are still in there. There's just as much sugar. It's just every time you take a sip, there's going to be a little bit less in comparison to what you'd get when it was concentrated. So in the dilution equation, we're trying to make sure that all our moles of our chemical are still there. Okay? And this liters should cancel out. Okay? And this is just a convenient way to do it, since usually we have our hands on this information. Now, as a result, whether you have liters or milliliters can kind of be a little bit flexible, but I like to convert it to liters just to make sure that my units cancel out correctly. So let's just plug some stuff in and trust our M1 V1 equals M2 V2. I should also say this is just basically a ratio. You don't really need to memorize this if you're good with ratios and being like, oh, okay, I've got this much of this much of that. If I change this, has this change, then you should be able to figure it out that way too. And I have had students do that in the past, but let's just try it. So this is going to change to 0.125 liters, and this is going to change to 0.5 liters. Okay, so our original solution was 2.0 moles of solute per liters of solution. Okay, and it was occupied in 0.125 liters of solution. So I could use that to figure out how many moles there are in this. I can also just say, well, hey, compared to after we go and dilute it, I had some unknown concentration I don't know, but the number of moles should still be the same there. Okay, and that should be in now 0.5 liters of solution. So all I have to do is solve out the math. I take 2 times 0.125, which should be 0.250. My units should be moles equals. This question mark is my molarity I haven't figured out yet, times my 0.5 liters. So if I do the math for this, I divide both sides by 0.5 liters, or I divide the 0.5 over. I think of it like that. That goes away. 0.25 divided by 0.5 should be just 0.5. Okay, my units are now moles per liter, so I got molarity back. So the concentration of my new solution is going to be 0.5 molar, which is what I have here. Let's take a look at these last three multiple choice problems. Okay, number 33, 500 milliliters of a 0.4 molar calcium nitrite solution contains how many moles of calcium ions and how many moles of nitrite ions? Well, calcium nitrite is CaNO2, 2. How do I figure that out? Well, calcium has a positive 2 charge. The nitrite ion has a negative 1 charge, or 1 negative charge, however you want to write that. So I would need 2 nitrites to cancel the positive 2 charge of the calcium. Okay, so there we go. So I've got CaNO2, 2. When this is dissolved, I don't really keep this as one big piece. Okay, when ionic compounds dissolve, they turn into their ions. So this is going to turn into a Ca2 plus ion floating around, and an NO2 minus ion floating around, and another NO2 minus ion floating around. Okay, so my concentration of all this stuff together is 0.4 molar, but that's going to kind of change when we kind of do some stuff around. So let's see what the concentration of this would be all together. If I take this 0.4 molar, which is just 0.4 moles per liter, and I multiply that by 0.5 liters, that's my 500 milliliters converted into liters. Okay, 0.4 times 0.5 should give me 0.2. My liters cancels out, should be moles. Okay, so I should have 0.2 moles of calcium nitrite, CaNO2, 2. Okay, now when I go and break up this calcium nitrite into its ions, okay, I'm going to have just as many CAs as I do CaNO2 2s. Okay, if I start with one of these CaNO2 2s, if I start with one calcium nitrite, I end up with one calcium ion. Another way you could think of it is kind of like a conversion problem. Okay, so if I have one CaNO2 2 times, I want to get rid of CaNO2 2. CaNO2 2, it goes on bottom. I want to know how many calciums I can get out of that. Well, for this conversion factor here, what's this relationship? Well, there is one Ca ion for every one CaNO2 2 ion. So one of these makes one of these. So I'm still just going to have 0.2 moles of Ca2 plus. On the other hand, I break this into 2 moles of nitrite. Okay, so if I have 0.2 moles of this starting out, I'm going to have twice as many nitrite ions floating around as I did the entire compound held together. So it's going to be 0.4 moles of NO2 minus floating around, okay, which is what B is telling us. Okay, so in total, I go from having 0.2 moles of stuff floating around to 0.6 moles of stuff floating around. Okay, 0.2 of those moles are calcium ions, and 0.4 of those moles are nitrite ions. When radium-226, this is number 43, when radium-226 is converted to radon-222, which of these is true? See, a neutron is released. We don't really kick neutrons out of the nucleus very often. a neutron is a pretty heavy particle, kind of like a proton. So it would take a lot to rip one of those out of an atom. So yeah, no, that doesn't sound like a good option, so we probably shouldn't look at 43's A. What about B, though? An alpha particles. I mean, you know, an alpha particle seems pretty fine. In fact, it should be. What's the answer? Did I mark another one wrong? I feel like that one should be B. Let's go check the magic answer sheet. 43. It is B. Why did I put C? Okay, no. An alpha particle. Man, I'm really running out of room here. An alpha particle is basically a helium nucleus with a mass number of 4 and an atomic number of 2. It's 2 protons and 2 neutrons clumped together. So it's positively charged, and it's just 2 protons, 2 neutrons, mass number of 4. So when you kick out or emit an alpha particle, that means your mass number goes down by 4, and your atomic number goes down by 2. Well, radium's mass number goes down by 4. In this case, it goes from 226 to 222. Okay, and its atomic number, well, radium is number 88. Radon is 86. So its atomic number goes down by 2. So yeah. Electron release or electron capture would involve our atomic number rather than our mass number. Our mass number should stay the same. Electron capture or electron release, like a beta emission, would be more like just changing the atomic number by 1, if I remember correctly. There's one more I'm not thinking of. There's electron capture, there's beta decay, there's alpha emission. There's something else that is very closely related to the beta stuff, the electron stuff. But for now, alpha particles is the one we need to worry about for this one. And finally, which of the following elements would be expected to be particularly stable based on neutron to proton ratios? Typically for smaller atoms, which means like not something with a mass number of like 40 plus, I would say. Or rather maybe an atomic number of 40 plus. Yeah, after like an atomic number of 40, we start to kind of get to a point where we have more neutrons than protons. Before that, with stuff with an atomic number below 40, we have a pretty good ratio of if we have this many protons, we have this many neutrons. So we should have about a ratio of 1 neutron for every 1 proton. So which has the closest ratio to that? Well, this carbon has 8 neutrons. If you subtract the mass number by the atomic number, what's left is the number of neutrons. 8 neutrons versus the 6 protons. 6 to 8 isn't bad, I guess. See, this is 17 versus 20 neutrons. This guy is 10 protons to 10 neutrons, which is a nice even 1-to-1 ratio. And this guy is 17 to, let's see, what, 22? 22 neutrons? So not too great. So the thing closest to a 1-to-1 ratio is our neon 20 isotope. Since it has a mass number of 20, if you subtract out the 10 protons it must have to be neon, what's left is 10 neutrons. And that's the multiple choice section. I'll make a separate video for the short answer.